Good morning, class. We're looking at exam 3 review, chapter 3 differentiation rules, chapter 4 application of differentiations. Exam 3 covers from 3.9 to 3.11, 4.1 to 4.5, and here's 4.3, how derivatives affect the shape of a graph. 4.4, indeterminate forms and L'Hopital's rule. 4.5, summary of curve sketch. So here's the summary how derivatives affect the shape of a graph. A function is increasing where f prime is positive. Function is decreasing where f prime is negative. So if you look at this one, it looks like a line with a positive slope, looks like a line, almost a line with a negative slope. A critical point definition, a critical point of a function is a point for which f prime is 0 or does not exist. DNE does not exist. A relative maximum or relative minimum is a critical point at the top or the bottom of an interval of a graph. A function is concave up where f double prime is positive. That means f prime is increasing, and it's concave down when f double prime is negative, meaning f prime is decreasing. So concave up, concave down. An inflection point, short IP, an inflection point C is a point where concavity changes. Inflection points occur where f double prime is 0 or f double prime does not exist. And as you can see, it's concave down here, it's concave up here. As the change occurs, it creates an inflection point. We want to graph functions. We need to remember what we did in previous courses, algebra courses, pre-calculus. One was the end behavior. Recall, the end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. So a polynomial f of x is in the form of a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0, where n must be a whole number all the way to 1, of course. This is called the leading term, and ultimately the graph will look like that. That is the concept of the end behavior. So if we have even function, if we have odd function, if the leading coefficient a sub n is positive, odd function looks like y or f of x equals x squared. If a sub n is negative, the leading coefficient looks like minus x squared. In the case of an odd power, the end behavior looks like f of x equals x cubed when the leading coefficient a sub n is positive, and when it's negative, looks like minus x cubed. Meaning, if you look at this case, of course, when x goes to positive infinity or x goes to negative infinity, in both cases, f of x goes to positive infinity, meaning the first and the second quadrant. On the other hand, here, whether x goes to negative infinity or positive infinity, f of x in both cases goes to negative infinity, which means the third and fourth quadrant. In this case, when x goes to negative infinity, so does f of x. When x goes to positive infinity, so does f of x, meaning the first and third quadrants are the end behavior. And this one is the other way around. When x goes to negative infinity, f of x goes to positive infinity. When x goes to positive infinity, y goes to negative infinity. Remember, f of x or y. And that means the end behavior is about the second and fourth quadrant. We also have a behavior near a 0 or near an x-intercept or near a root. Multiplicity m. X minus c, the 0x minus c, has multiplicity m because it's being raised to the power of m. If m is odd, f crosses the x-axis at c0. If m is even, f does not cross the x-axis at c0. So looking like that. Those are some examples. This is a single zero. This is double zero. Multiplicity even or two. This is multiplicity three. Now, the higher the multiplicity, the flatter the curve is at the zero. The sum of the multiplicities is the degree of the polynomial function. So we went over this, so be able to graph this first and foremost with prior knowledge of mathematics. Okay, but steps to curve sketching, in addition to algebra or pre-calculus, we want to find the relative max and mean and intervals where the function increases and decreases. And the setup is we set f prime of x equal to 0 and solve for x and make a sign graph. F prime is 0 or f prime doesn't exist. Then we want to find inflection points. Well, so we set f double prime equal to 0 doesn't exist and solving for x and b. And then make a sign graph for IPs and concavity and sketch the graph. So first, I want to remind you how to graph this using just prior knowledge of mathematics. To graph this, we want to go with the intercept. So we're going to factor out the negative x. So we get negative x times x squared minus x minus 1. And we are going to set this equal to 0. When we set this equal to 0, this one, x is 0, this one, we can do the factoring. We have to use the quadratic formula, x is minus b plus minus a squared of b squared minus 4ac over 2a. So this part a is 1, b is negative 1, c is negative 1, and we plug in to this formula minus b minus negative 1 makes it positive 1 plus minus the square root of b squared minus 1 quantity squared minus 4 times a, which is 1 times c, which is negative 1 over 2 times a, which is 2 times 1. This is positive 1. This is positive 4. They add up to 5. Therefore, we have the following x-intercepts. This one is 0, so 0, 0. This one, 1 plus square root of 5 divided by 2, and 1 minus square root of 5 divided by 2, comma, 0 in both cases. Now, what I want to do, I want to show you how to graph this without more details, just the way we have it. This is not to scale. So 0, 0 is here. Now, square root of 5 is about 2.2, with 1 is 3.2, divided by 2 is almost 1.6. The reason I say that because of graphing. So a rough sketch gives us this point, and this one gives us negative 0.6. That gives us this point. And here's the leading term, that is the end behavior, which means like so. So if I were to graph that, it should look something like this. I hit this x-intercept, I have to come back up at some point. I hit the other x-intercept, I have to come back down at that point. And in all of these three cases, the graph crosses the x-axis because each one has a multiplicity 1. This one, multiplicity 1, multiplicity 1, multiplicity 1. And so this is a rough sketch using prior knowledge of mathematics. Let's make this with more details by looking at f prime and the first derivative test. So f prime of x is negative 3x squared plus 2x plus 1, and we are going to set this equal to 0. That means I'm going to first factor a negative sign. So it makes it easier to factor. We have no choice but to go with x and 3x because 3 is a prime number. So that makes it easy. and -1 is one of them is 1, one of them is -1. We want to make sure the middle term works. This is -3x, this is positive x. They add up to -2x, this one, and that works. So x is either 1, where you set this equal to 0, or -1/3. So how do you do the first derivative test? A number line that goes from negative to positive infinity. You put the critical points where f prime is 0 or f prime does not exist in order from smallest to larger. So you put -1/3 first, then 1. At -1/3 you get 0. F prime is 0. At 1 is 0. And f prime doesn't exist, doesn't give us any solutions because f prime itself is a polynomial of degree 2. Now you use TPs, short for test points. The easiest point in between would be 0. To the left would be -1. To the right would be +1. Please understand, -1/3 and 1 in between is 0, right? To the left, -1, to the right. So you can test point those. If you plug in 0, and it's easier to go here, you get +1, so it's positive. We are interested in the sign. We don't want necessarily a number. +10 or +5 makes no difference. It's positive. Now, they will alternate. You don't have to evaluate the rest of them. The reason they alternate, because this is degree 2 and it has 2 solutions. That means each one has a multiplicity 1 or odd. However, if you have any doubts, just plug in -1 or 1 and test. If I plug in 1, I get -3 here. If I plug in 1, I get -3 plus 2. Just plug in 2 because it's to the right of 1. To the left was -1, to the right of 1 is 2. That would be the test one. If I plug in 2, I get 4 times -3 is -12. Plus 4 plus 1, that means +5. -12 plus 5 is -7, makes it negative. Now let me throw in the arrows. Arrow down, arrow up. What does it mean? Arrow down, arrow up, local mean. Arrow up, arrow down, local max. And so local minimum occurs at this point. We have to plug it back into function to find the y-coordinate. Local max occurs at this point. You have to plug it in. When we plug this in, this becomes 1. This is easy to see. Therefore, local max is 1 at 1, 1. Again, plug in. Local max is the y-coordinate. Let's plug in -1/3 and evaluate it in the original function f of x. Now, as you can see, this is a -1/27. This makes it positive. And this is positive 1/9, and this is -1/3. Now, clearly 27 is a common denominator. Therefore, this is 3/27. This is 9/27. So 1 plus 3 minus 9 makes it -5/27. And we write local minimum is -5/27 at the pair -1/3 and -5/27. Now, positive means increasing, so it's increasing from -1/3 to 1. Negative means decreasing from -infinity to -1/3 union 1 to infinity. Now, since I have to continue, I'm going to just repeat what I had in the previous page, meaning I have my function, I have f prime, I have my intercepts, maximum, minimum, increasing, decreasing. This is all the knowledge from the previous page. There's nothing brand new here. So I'm going to go with the inflection point. To find inflection point, I'm going to go with f double prime. So differentiate this and you get -6x plus 2. You set this equal to 0 and you get 1/3. I hope everybody's comfortable with that concept. So you go with the sine graph, and here's a number line from negative to positive infinity at x equals 1/3, f double prime is 0. you find where f double prime is 0, where f double prime does not exist. So f double prime exists everywhere because it's a polynomial of degree 1 or a linear function. So test point to the left, of course, the easiest point would be 0, right? TP, I'm going to call it, short for test point 0. Over here is 1. And if you plug in 0 into f double prime, you get positive 2. So this is positive, it will alternate. If you have dots, plug in 1 and you'll see that. So what does it mean? Positive means concave up from negative infinity to 1/3. Negative means concave down from 1/3 to infinity. Because of the change, inflection point takes place at 1/3. Put it back into the original function and evaluate. 1/3 cubed is 1 over 27. Negative makes it negative. This is 1 over 9. This is 1 over 3. Again, 27 is a common denominator. So this becomes 3. And this becomes 9. 3 and 9, 12 minus 1 is 11 over 27. The inflection point takes place at 1/3 comma 11 over 27. And so we have the table. This is the synopsis of what we have done. There is nothing brand new here. So I just like to summarize what we find. For example, x-intercept is 0, 0. So right here. And the next one, 1 minus square root of 5 over 2 is about negative 0.62. The reason we go with the decimal for the sake of graphing. Okay, so negative 0.62 is somewhere here roughly. Again, doesn't have to be to scale. 1.62, 1 plus square root of 5. We go with the approximation again for the sake of graph is somewhere here. Maximum takes place at 1, 1. Here's 1, here's 1. Put them together. And because we said it's max and it exists, and therefore it's a horizontal tangent line, at that point we put a double-sided arrow, meaning the graph can't cross that. IP is located at this point, and here's an approximation again for the sake of a graph, roughly 0.3 and roughly 0.4. So somewhere here and somewhere here. And when we put them together again, it doesn't have to exact, it's close, okay? And minimum takes place at negative 1/3, negative 5 over 27. Again, I go with the approximation for the sake of graph. So minus 0.3 somewhere here, minus 0.2 somewhere here. Put them together, you have that. And because we said it's a minimum, again, we go with the double-sided arrow, meaning it can't cross it when we do the graph. Remember, this is the leading term. So the second and the fourth quadrants, and that's the graph. As you look at the graph, you see where the function is decreasing, where the function is increasing, where the function is decreasing. You see the function is concave up and then concave down. You see the inflection point. You see all your intercepts, local mean, local max. All the information is here. 4.4, indeterminate forms and L'Hopital's rule. Limits of the following forms are indeterminate forms. An indeterminate form of type 0 over 0, an indeterminate form of type infinity over infinity, meaning we don't know what will be the answer. We can't assume it's 0 or infinity or a specific number. We have to work it out. Example, the limit of ln x over x minus 1 as x approaches 1. If you plug in, you get ln1, which is 0. You get 1 minus 1 over 0. So this is 0 over 0. So that's an indeterminate form. Infinity, ln of infinity is infinity. X minus 1 as x approaches infinity. So it's infinity over, by the way, infinity minus 1 obviously is infinity. So those are indeterminate forms. So according to L'Hopital's rule, this is what we have, which says, suppose f and g are differentiable and g prime is not equal to 0 on the open interval of I that contains a except possibly at a. Suppose that the limit of f of x as x approaches a is 0, limit of g of x as x approaches a 0, or limit of f of x as x approaches a is either positive or negative infinity, g of x is positive or negative infinity, and then in other words, we have an indeterminate form of 0 over 0 or infinity over infinity. And this limit, the limit of f of x over g of x as x approaches a, is the same as the limit of f prime of x over g prime of x as x approaches a. Please do not mix this up with the quotient rule of differentiation. We say we take the derivative of the top, we take the derivative of the bottom, and it works. Of course, if the limit of the right side exists. So the limit of f of x over g of x, if you show it's 0 over 0 or infinity over infinity, then you can use the L'Hopital's rule and say it's limit of f prime over g prime as x approaches it. That's the bottom line. That's called L'Hopital's rule. We have other indeterminate forms. We'll discuss them as we come across them. Indeterminate form of type 0 times infinity. In that case, we write fg as a quotient, fg as f over 1 over g, or g over 1 over f. It makes, one of them makes 0 over 0, one of them makes infinity over infinity, and you have to decide which one makes your life easier. Here's a simple example, the same thing we saw in the previous page. Remember, if you plug in and you first have to show it's 0 over 0, therefore you can use the L'Hopital's rule. So it's the same as taking the limit as x approaches 1 of the derivative of the top is 1 over x, the bottom is simply 1. Again, h is representing the L'Hopital's rule. So because it's 0 over 0, I can use the L'Hopital's rule. And you know this is the limit of 1 over x as x approaches 1, which is equal to 1. Here's another example. Let's plug in 0. If I plug in 0, I get e to the power of 0 minus e to the power of 0 minus 2 times 0 over 0 minus sine 0. And I hope you recognize e to the power of 0 is 1. So e to the power of 0 minus e to the power of 0 is 0. We end up with 0 over 0. Because it's 0 over 0, I can use the L'Hopital's rule, meaning I'm going to differentiate this. I get e to the power of x. I'm going to differentiate this. I get minus e to the power of x, but this becomes plus. I'm going to differentiate this. I get minus 2. That's for the top. I'm going to differentiate this. I get 1. Minus, I'm going to differentiate this. I'm going to get cosine x. So differentiate the top, differentiate the bottom. It is not the quotient rule of differentiation. And plug in. When we plug in, what happens? I hope you see that you get e to the power of 0 plus e to the power of 0 minus 2. Just right away, the numerator is 0 because e to the power of 0 is 1. And the bottom is 1 minus cosine of 0. 1 minus 1. So you get 0 over 0, meaning you can do it again. When I differentiate the top, I get e to the power of x, and this one gives me minus e to the power of minus x, and this gives me 0. This one goes away. The derivative of cosine is negative sine. The derivative of negative cosine is positive sine. Let's plug in e to the power of 0 minus e to the power of 0, and obviously the top is 0. Sine of 0 is 0. And again, same situation. We can continue with the L'Hopital's rule. This gives me e to the power of x. This gives me plus e to the power of x, and this gives me cosine. And now if you plug in, you get e to the power of 0 plus e to the power of 0 over cosine 0. And I hope you recognize the top is 1 plus 1. the bottom is 1, and the answer is 2. So that works out after taking the using the L'Hopital's rule several times. Now remember what you have to do. First and foremost, you plug in everybody. So if I plug in pi over 2, okay, and this is cosecant of pi over 2. Now, the numerator is 1 minus 1, right? The denominator, cosecant, is 1 over sine. So the numerator is 0, the denominator is 1. The answer is 0. That means we don't have to use the L'Hopital's rule, and that is important to understand. First, you work it out, and then you see if you can use it. Use the L'Hopital's rule or not. What do we do here? There are two ways to approach that. If you plug in, you get 0 over 0. I'm going to leave it for you to prove that. What did we do before? We factored. So x minus, we are hoping, remember, x approaching to x minus 2 is a problem. So you can take the x minus 2 out. You get x plus 3, and the limit when you plug in 2, it's 2 plus 3 or 5. This is what we did before, and we can always do that. However, because it's 0 over 0, we can use the L'Hopital's rule, and that means we are going to differentiate the top. We get 2x plus 1, and the bottom gives you 1. And if I plug in 2, I get 4 and 1, 5 over 1, which is 5. So both of them are the same. Now that you have the luxury of using L'Hopital's rule, you have a choice. Limit of ln of squared of x over x squared. I hope you realize this is ln of infinity, which is infinity. This is infinity squared, which is infinity. So you have infinity over infinity. Therefore, we are going to use the L'Hopital's rule. There are two ways to do that. First of all, this one is 2x, this one. By now, you know, you can write this as 1 over square root of x and then times 1 over 2 squared of x. So you can do that. Or a faster and easier way to remind you again would be to change this to x to the power 1/2 and write the numerator as half of ln x. And this, when you differentiated half of 1 over x. Okay, let me just show you if I were to go this route and use h, then I would say the limit as x approaches infinity, the numerator is 1/2 times ln x gives me 1 over x, and the denominator gives me 2x. Either way, I hope you recognize this one. The numerator is 1 over 2x, okay, which is the same as that. Anyways, it's 1 over 4x squared, and so 1/2 times 1 over x if you go that route. And it's 1 over 4x squared, which results in 0. Again, this would have been actually a better methodology. The square root of x perhaps is easy enough, you can do that, but always simplify using the knowledge of properties of logs. We want to find the limit of x times ln x as x approaches 0 from the right. We know the L'Hopital's rule. Indeterminate products, reminding you, indeterminate form of type 0 times infinity, rewrite the product fg as f over 1 over g or g over 1 over f. First of all, if you plug in, this is 0, this is ln of 0 from the right. I hope you remember it's negative infinity from the graph. And again, I quickly remind you. Remember the graph. And that's why we have this. So now it's in the form, and 0 times negative infinity, you don't know what the answer is. You can't assume it's 0, and here's the reason. When we say 0, remember, if it's 0, the answer is 0, but it's approaching 0. It's really not necessarily getting to 0. So there's a struggle between the two. Does this approach 0 before this approaches infinity, or this approaches infinity on the negative or positive side before it approaches 0? And interesting things happen. It can go to 0, it can go to infinity, or somewhere in between, negative infinity or somewhere in between. That's the concept. So you can take one of them down, and since it's going to be hard to deal with ln x taking it down, we're going to take x down and we're going to make it 1 over x. And now if you plug in, this is still negative infinity. Now 1 over 0 from the right is positive infinity. So now you have to go with this format or this format before you can use L'Hopital's rule. Now we can use the L'Hopital's rule. And to use the L'Hopital's rule, the top one gives me 1 over x, and the bottom, by now we know it's negative 1 over x squared. If we don't, we can work it out. Let me quickly show you. So for this one class, we should know 1 over x equals x to the power minus 1. Its derivative is minus x to the power minus 2. Okay, we should know that. And simplification of this complex fraction will result in minus x, and the limit is therefore 0. The limit of the square root of x times e to the power minus x to the power of 2. If you plug in infinity class, square root of infinity is infinity. Now, e to the power of infinity is infinity, but e to the power of minus infinity, or minus infinity divided by 2 makes no difference, is 0. Please understand, because of the negative sign. E to the power of minus infinity divided by 2 is 0. So now we have to take one of them down. It's easier to take this down and make it positive exponent. And I hope you realize, if I put infinity, square root of infinity is infinity. And if I put infinity, e to the power of infinity over 2, or infinity times anything, becomes infinity. And now we can use L'Hopital's rule. We've seen this many times before. By now, we know the derivative of square root of x is 1 over 2 square root of x, or you can do the math. And e to the power of x over 2 is itself times 1/2. This is e to the power of half of x. So this is 1 over 2 square root of x. This is itself divided by 2. Again, we should be comfortable with differentiation by now. So what happens is we do the complex fraction. 1 times 2 goes to the top, 2, and 2 square root of x times e to the power of x over 2 goes to the bottom. 2 and 2 cancel each other. Or you may recognize that right away here, and you say, okay, this 2 is in the denominator of the numerator. This 2 in the denominator of the denominator, you can cancel. And as you can see, when x approaches infinity, this is infinity, this is infinity, the product is infinity, 1 over infinity is 0. Indeterminate differences type infinity minus infinity. Try to convert the difference into a quotient by using a common denominator or rationalization or factoring out a common factor so that we have an indeterminate form of type 0 over 0, infinity over infinity. In other words, the only way we can use L'Hopital's rule if it's 0 over 0, the result, or infinity over infinity. So, for example, the limit of cosecant x minus cotangent x as x approaches 0 from the right. If you plug it, by the way, cosecant is 1 over sine. Uh, Cotangent is cosine over sine, and I hope you know that each one is infinity. So it's infinity minus infinity class. The format is infinity minus infinity. 1 over sine, cosecant is 1 over sine. Sine goes to 0, 1 over sine goes to infinity. You may know that cotangent of 0, if you remember the graph of a cotangent, looks like y equals minus x cubed, but one of the vertical asymptotes is the y-axis or x equal to 0. I hope you remember the graph. So it's infinity minus infinity. So the technique is to write this as those. And now there's a common factor of a common denominator of sine x. So we get 1 minus cosine over sine x. And now if we plug in, cosine of 0 is 1. So 1 minus 1 is 0. Sine of 0 is 0. So we get 0 over 0. Therefore, we can use the L'Hopital's rule, which means we're going to write the limit as x approaches 0 from the right. We're going to differentiate the top. This goes away. Minus cosine gives you positive sine. Sine gives you positive cosine. And since x is approaching 0, you get sine of 0 over cosine of 0, which is 0 over 1, which is 0. The limit as x approaches 1 from the right of ln of x to the power of 7 minus 1 minus ln of x to the power of 5 minus 1. So if you plug in 1, you get ln of 0. Of course, it's from the right. That means ln of 0 from the right. So this is, remember I gave you the graph. This is negative infinity. Same thing happens here. Negative infinity with the negative in front. Minus infinity minus negative infinity. So it's minus infinity plus infinity or infinity minus infinity. Okay. Let me just write that in case if anybody needs to see that. So this in essence is minus infinity plus infinity, the same as this one. And so we have to use some sort of a technique. So I hope you see that we can combine these two using the quotient rule becomes ln of x to the power of 7 minus 1 over ln of x to the power of 5 minus 1. And we can interchange natural log and limit because as x approaches 1 from the right makes two functions continuous. That means that is part of the domain. And if you look at this one, if you plug in 1, let's see what happens. You get ln, and this one, if you plug in 1 from the right, this becomes 0, this becomes 0, but 0 from the right in essence. So ln of 0 over 0. So inside, because it's 0 over 0, we can use L'Hopital's rule. So ln of now, limit as x approaches 1 to the right. This becomes 7x to the power of 6. This becomes 5x to the power of 4. And now if I plug in 1, this gives me 7, this gives me 5. So ln of 7 over 5 is the precise answer and the final answer. find the limit of secant x minus tan x as x approaches pi over 2 from the left. First, notice that secant x goes to infinity and tan x goes to infinity. We are saying pi over 2 from the left. One easy way to understand that, think about pi over 2 as 90 degrees, from the left like 89 degrees, 89.99 degrees, as x approaches pi over 2 from the left. So we end up with a limit that is indeterminate form of infinity minus infinity. I hope you remember the graph of tan x, and secant is 1 over cosine. Remember, cosine of pi over 2 is 0, if that helps. So anyways, what is the technique? Secant is 1 over cosine, 1 over cosine, and tangent is sine over cosine. So 1 over cosine minus sine over cosine, which makes it 1 minus sine over cosine. So the limit of this expression as x approaches pi over 2 from the left. Now, if we plug in pi over 2, we get 1 minus sine of pi over 2 over cosine of pi over 2, which makes it 0 over 0, because cosine of pi over 2 is 1. And because it's 0 over 0, then we can use the L'Hopital's rule. We differentiate the top, so limit as x approaches pi over 2 from the left of, now the numerator, 1 minus sine x becomes minus cosine x becomes minus sine x. And this is the limit of tan x. Cotangent x. My apologies. Cotangent x. As x approaches pi over 2 from the left, and that makes it 0. When x approaches pi over 2 from the left, tangent goes to infinity, but cotangent goes to 0, because you can think of it as 1 over infinity. That's one. Remember, cotangent is 1 over tangent. Or think about remember the graph again looks like this. A quick reminder might be helpful. So this is, okay. The graph of tan x. With those vertical asymptotes. I just gave you one cycle. And this is x equals 0. This is x equals pi. And this is pi over 2. And this is y equals cotangent. So as far as reminding everybody about the graphs. All right, we have indeterminate forms that are indeterminate powers. Several indeterminate forms arise from the limit of f of x to the power of g of x as x approaches a. Limit of f of x as x approaches a is 0, limit of g of x as x approaches a is 0. In other words, we could have 0 to the power of 0. Limit of f of x as x approaches a is infinity, we can have infinity to the power of 0. Limit of f of x as x approaches a is 1, but limit of g of x as x approaches infinity is plus minus infinity. So 1 to the power of infinity or 1 to the power of negative infinity. Those are also considered indeterminate. And what do? Each of these three cases can be treated either by taking a natural log. So if I take the natural log of the form this expression f of x to the power of g of x, then g of x, if I take a natural log, g of x sits in front and becomes a coefficient. So ln y is g of x, ln of f of x. And so I go through the process and I find the limit for ln y as something, for example, k. Then what would be the answer to this one would be e to the power of k, the reverse process. Well, if this is 5, this is e to the power of 5. This is 10, e to the power of 10, minus 2, e to the power of minus 2. Okay, that's one way. Or by writing the function as an exponential format, f of x to the power of g of x, you replace f of x with e to the power of ln of f of x. And then so you get e to the power of g of x times ln of f of x. In either method, we are led to the indeterminate product g of x times ln of f of x. Take a look. Over here, we have this one to work with. Over here, we have this one to work with. Which is the type 0 times infinity or infinity times 0. So if we go this route, we said the answer is e to the power of k. This one already gives you e to that power. So either way works out as long as you know what you're doing. So for example, the limit of 1 plus sine for x to the power of cotangent x as x approaches 0 from the right. When x is 0, 4x is 0, sine becomes 0, so this is 1. And cotangent of 0, if you recall, the graph looks like almost y equals minus x cubed. So that one is infinity. So we have 1 to the power of infinity. We are going to, in order to make life easy, we're going to call this expression something. For example, y represents 1 plus sine 4x to the power of cotangent x. Now we're going to take a natural log of y and work on it. And whatever the answer is, then the final answer for this one would be e to that power. So we're going to take the natural log of the left and natural log of the right, and cotangent becomes a coefficient. So cotangent sits in front. So ln y is cotangent x times ln of 1 plus sine 4x. We are going to look at the limit of ln y as x approaches 0 from the right. So we're going to take the limit of this expression, which is ln of 1 plus sine 4x over tan x. The reason we write it as this format, because if you plug in 0, of course, you get ln of 1, which is 0, and tan of 0. So you get, if you plug in, okay, if you plug in, you get ln 1 over tan of 0, which is 0 over 0. Now we can use the L'Hopital's rule. That's the idea behind this concept. Why are we doing this? So we can use the L'Hopital's rule on that. So if I want to use L'Hopital's rule, that means I'm going to write the limit as x approaches 0 from the right. I'm going to take the derivative of the top over the derivative of the bottom. So how do I take the derivative of the top? Since I see a natural log, I'm going to flip this over, make it 1 over 1 plus sine 4x, and then times the derivative of the expression, which is sine becomes cosine 4x times 4, cosine 4x times 4, and the bottom tan gives me secant squared. You can simplify this complex fraction, or you can just plug in. Either way is fine. If I plug in 0, I get 4 cosine 0. Cosine 0 is 1. So 4 times 1 is 4. Sine 0 is 0. Secant is 1 over cosine. So 1 over cosine of 0 is 1. So secant of 0 is 1. So 1 squared is 1. So what you have is 4 divided by 1. 4 divided by 1 is 4. Again, that would be a sort of fast way to handle it, everybody. So what is the, if this is 4, this limit is e to this power. The limit of this expression is the limit of y as x approaches 0 from the right, which makes it the limit of e to the power of ln y as x approaches 0 from the right, or simply e to the power of. You don't, I mean, this is really, believe it or not, is justification of why it's e to the power of 4. However, we've done that before, and we can say whatever the answer is, e to that power. It's the final answer. Summary of curve sketching. Definition: vertical asymptote VA, horizontal asymptote HA. We have a rational function f of x in the form of n of x over d of x. N represents the numerator, d represents the denominator. The numerator is a sub n x to the power of n all the way to a sub 0. The denominator is b sub m x to the power of m all the way to b sub 0. N of x and d of x are both polynomials. D of x, the denominator, can never be 0. And the domain is whatever you have to exclude here. D of x cannot be 0. Now, VA, short for vertical asymptote, x equals a, if the limit of f of x as x approaches a from the left or from the right is either negative or positive infinity. The graph of a rational function never crosses a vertical asymptote. It may intersect a vertical asymptote. Simplify. If you have this one simplified in its lowest term, so there is no common factor between the top and the bottom, then the VA is d of x equal to 0, which gives you the equation of x equals a. This is a faster way to find it, where the limit of f of x as x approaches a is a positive negative infinity. Limit of f of x as x approaches a from the left is positive negative infinity, or from the right, then x equals a is the vertical asymptote. This is the formal definition of a vertical asymptote. Simply put, this is, and you have to use that for various functions. For rational functions, you set the denominator equal to 0. It is important to make sure it's in lowest term, because if there's a common factor between the top and the bottom, you have to exclude the bottom from the domain. However, it is not a vertical asymptote. Horizontal asymptote has the following definition. Horizontal asymptote, or HA, of the curve y equals f of x is y equals L if the limit of f of x as x approaches negative infinity is L, or limit of f of x as x approaches infinity is L. That's the definition. So the graph of a rational function may or may not cross a horizontal asymptote. Again, horizontal asymptote has this definition. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. And definition of an oblique, also known as slant asymptote, OA or SA. It has the equation y equals mx plus b if the limit of f of x as x approaches negative or positive infinity is mx plus b. So let's put these two together. Here's the synopsis of that. So we have this function in its lowest term, okay? If n is less than m, if the degree of the numerator is less than the degree of the denominator, horizontal asymptote y equals 0. I hope you remember that from previous courses. If n is equal to m, if they have the same degree, then the leading terms take over, and we get a sub n over b sub n, y equals that. If n is precisely n plus 1, then we do the division using the long division or a synthetic division. We get mx plus b, which is a first degree, and then the remainder. This one, y equals mx plus b, is your oblique asymptote. So the difference of degree must be precisely 1. That's why we get a linear function. So for example, we want to find all the asymptotes for this function. F of x is x squared minus 4 over x minus 1. First and foremost, make sure it's in its lowest term. There's nothing in common between the top and the bottom. So VA would be x minus 1 equal to 0, or x equals 1. Horizontal asymptote, we don't have any, because the degree of the numerator is 2. The degree of the denominator is 1, which makes it larger than the denominator. So there is no horizontal asymptote. However, the difference of exactly 1 means we have slant asymptote. We are going to do division. I'm going to assume everybody can do that, but quick explanation. of the long division, you divide the first one by the first one, gives you x. You multiply x here, you get x squared minus x. And then you change the sign. You say this is negative, this is positive because you're subtracting. And this gives you x minus 4. And then you divide x by x, and it gives you positive 1. You multiply the x minus 1, you subtract, and you're done. So x plus 1 is your quotient. So y equals x plus 1 is your slant asymptote. We want to sketch the graph of f of x equals x minus 1 over 2x plus 1 with a little bit more details than what we have done in pre-calculus or college algebra by adding the information from calculus. So first, let's get the information from prior knowledge of mathematics. Intercept. How did you find the x-intercept? You set y equal to 0. Y or f of x is 0 when the top is 0, x becomes 1. Again, x-intercept, set y or f of x equal to 0. A fraction is 0 when the top is 0. X minus 1 equal to 0 gives you x equals 1, 1, 0. Y-intercept, you replace the x with 0, you get minus 1 over positive 1, which is negative 1. So this is 1, 0. This is 0, negative 1 again. F of 0. If I plug in 0 here, I get minus 1 in the numerator, positive 1 in the denominator. The result is negative 1. 0 minus 1. Locate that, put it there. 0 minus 1. Asymptotes. The easy one would be the vertical asymptote, 2x plus 1 equal to 0, which results in x equals negative 1/2. X equals negative 1/2 is a vertical line. Okay. Horizontal asymptote. If you look at the degree of the numerator is 1, the degree of the denominator is 1. So 1 times x, 2 times x, y equals 1/2. Because the degree, because we have a horizontal asymptote, we don't have a slant asymptote. We have only one of them, class, not both. So y equals 1/2 because in essence, this is 1 over x over 2 over x, okay? They have the same degree. So y equals 1/2 is a horizontal line. So we have x equals negative 1/2, y equals positive 1/2. Let's look at the derivatives and domains. The domain is all real numbers. Go back to the vertical asymptote. That's the thing. All numbers except this one. You're going to exclude negative 1/2. So how do we write it in an interval format? Negative infinity to negative 1/2 union negative 1/2 to infinity. Now we want to take the derivative because we want to look at local extrema and so forth. So to differentiate this, it's pretty simple. We use the quotient rule. F prime g minus g prime f over g squared. I'm going to use the formula. See, I write the formula from the memory and I use that. So 1 times 2x plus 1 minus the derivative of the bottom is 2 times x minus 1, and then put the denominator in a parenthesis and square it. All you have to do is simplify the numerator. Again, notice it's 1 times 1 times 2x plus 1 minus 2 times x minus 1 and the bottom square. So we have 2x plus 1 minus 2x plus 2. So the numerator is 3. Now let's do the sign graph for that. And before we do the sign graph, you may recognize that this is a fraction with the denominator having an exponent which is even. It doesn't matter 2 or 20. And the numerator is a positive number. So this is always positive. You look at the bottom. The bottom is always positive, except when it becomes 0 at x equals negative 1/2. So you can right away say it's from negative infinity to negative 1/2 union negative 1/2 to infinity. So right here you're done, okay? Because it's always positive except at x equals negative 1/2. If you were to do the sign graph at negative 1/2, this is undefined, everybody. And to the left of negative 1/2, pick negative 1. To the right, pick 0 for the test. And if you plug in 0, you notice it's positive. You plug in negative 1, it becomes negative. Square, it becomes positive. So therefore, you're going to write, there's no extrema, okay? Because we don't, they have to change from positive to negative or negative to positive to create extrema. But it is increasing always because it's positive from negative infinity to negative 1/2 union negative 1/2 to infinity. Okay, so we want to go to the inflection point, continue with calculus. F prime is this. We're going to write it to the power of -2 because we want to differentiate it. It makes it easier. I hope you recognize that if I want to differentiate this, let me show you. I get f double prime is 3 times -2 times 2x plus 1 to the power of -2 minus 1, right? Because you have to go down. And then by the chain rule, the derivative of 2x plus 1, which is 2, and it makes it -12 over 2x plus 1 cubed. Again, this expression now, this expression will change, but it is f double prime equals 0, or like f prime is 0 doesn't produce any solution because this was a number, this was a number. But f prime is 0 or f double prime, f prime doesn't exist or f double prime doesn't exist, give us the same answer, x equals -1/2. So we're going to do the sign graph with the -1/2. So here's what happens, everybody. From negative infinity to positive infinity at -1/2, this is undefined. And to the left of -1/2, you have a test point, let's say -1. To the right, you have 0. If you plug in to this, 0 is easy, makes this one positive, so this is negative. -1 makes this one negative, and to the power of 3 still keeps it at negative. -12 over negative makes it positive. So positive means concave up from negative infinity to -1/2. Negative means concave down from -1/2 to infinity. And normally the change gives us an inflection point. However, why is it that we don't have an inflection point? Because -1/2 is not part of the domain. Okay, and so these are the 2 points that we have. Let's check before we graph, let's check if f crosses its horizontal asymptote. You must check f of x and horizontal asymptote. Sometimes they cross. So this one, set it equal to this one, 1/2. Now you do the cross product. You get 2 times x minus 1. So this is 2x minus 2, and this is 2x plus 1. As you can see, negative 2 can't be. This is a false statement. Okay, class minus 2 equals 1. It's a false statement. Doesn't produce any solution. That's why. Um, I want you to know when you graph a rational function, you have the asymptote. So either you have it here or here, because we have these 2 points, we have them here. And then on the left side of this vertical asymptote, either we have them here or here. Because we don't have an x-intercept, we should know it's here, but you can pick up another point. For example, if you plug in -1 into this, and -1 and -1 gives you -2. This gives you -2 plus 1, -1 gives you +2. And so it's this point. And now if you graph it, looking like that, and it's done. So you have all the details. You have this one, you have this one. The function is increasing, as you can see here, decreasing here. My apologies, it's increasing here, also increasing here. There is no extrema, there is local max, no local max, no local mean. Okay. It's concave up here, concave down here. So all piece of information that we got works here.